Imagine a time when the universe was a dark, foggy void, a mere 330 million years after the Big Bang. This was the cosmic dawn, an era shrouded in mystery. But now, NASA's James Webb Space Telescope has spotted a galaxy that defies all expectations. A galaxy so ancient it should not exist as we see it. Hello everyone, you're watching PhysxX Space, and today we are diving into Wave's groundbreaking discovery of JWST-131, a cosmic rebel that challenges everything we thought we knew about the early universe. To understand why this discovery is so shocking, we need to rewind 13.8 billion years after the Big Bang. The universe cooled into a fog of natural hydrogen gas, a period called the Cosmic Dark Ages, where light from the early stars and galaxies struggled to escape. For hundreds of millions of years, this fog blocked the ultraviolet light from escaping galaxies. But then something happened. The epoch of reionization. Massive stars and black holes began ionizing the hydrogen, carving transparent bubbles in the fog. By 1 billion years after the Big Bang, the fog had lifted. Or so we thought, until Webb peered deeper than ever before. For decades, telescopes like the Hubble gave us hints about this era. In 2016, Hubble spotted galaxies like GN-Z11, galaxies up to 400 million years after the Big Bang. Already impressive, but not enough to see the fog's lifting in action. As Hubble's vision was limited, it could not see through the densest part of the hydrogen fog or capture the faintest light from the earliest stars. That's why scientists pinned their hopes on the James Webb Space Telescope, a machine built to see the unseeable. Launched in 2021, JWST is a time machine. Its infrared eyes peer deeper into space and further back in time than any telescope before it. To grasp why JWST's discovery is revolutionary, we need to understand how it works. Unlike Hubble, which primarily sees visible and ultraviolet light, JWST detects infrared wavelengths. This is critical because light from the early universe is stretched into the infrared by the expansion of space, a phenomenon called redshift. The further away the galaxy is, the more its light is redshifted. JWST's crown jewels are two instruments: NIRCam, its primary camera, and NIRSpec, a spectrograph that splits light into wavelengths to reveal a galaxy's composition, temperature, and motion. In 2023, the JWST's Advanced Deep Extragalactic Survey JWST team used these tools to stare for 32 hours at a patch of the sky near the Hubble Ultra Deep Field. What they found stunned them. Among the galaxies in this field was Jade's GS Z13-1, a red tiny smudge in NIRCam's image. But when NIRSpec analyzed the light, the data revealed a redshift of Z13, meaning we're seeing a galaxy that existed just 330 million years after the Big Bang. The galaxy's redshift of 13.0 places it at the edge of the observable universe. That alone would have been groundbreaking. JWST had already broken its own distance record with galaxies like Macy's Galaxy Z11.4 and Glass Z13, Z13.2. But Jade's GS Z13-1 held a bigger secret: a bright Lyman-alpha emission line in its spectrum. Lyman-alpha light is an ultraviolet wavelength emitted when hydrogen electrons drop energy levels. But during the cosmic dark ages, neutral hydrogen should have absorbed this light like a sponge. Finding it in a galaxy this early is like seeing a flashlight through a brick wall. As Dr. Joris Wittstock, lead author of the case study, said, this galaxy is doing something we didn't think was possible yet. It's clearing its own path through the fog. Jet's GS Z13.1 isn't the only galaxy shaking up our models. Since 2022, JWST has discovered dozens of galaxies from the universe's first 500 million years, many more than simulations predicted. Some, like CEERS 93316 Z16.4, claim even higher redshifts, though these are still debated. But like glass Z13, show mature structures like spiral arms far earlier than expected. But JAIR's GS Z13-1 stands out because its Lyman-alpha emission defies the physics of dark ages. So, how did JAIR's GS Z13-1 pierce through the fog? Astronomers are scrambling for answers. Two leading theories are: number 1, ultra-bright first stars, population 3. These hypothetical stars, hundreds of times the Sun's mass, could have ionized local hydrogen bubbles. They're also some of the first stars in the universe called population 3 stars. They were likely giants, 100 to 1,000 times the mass of the Sun. These stars would have burned ferociously, emitting torrents of ultraviolet light. If JAIR's GS G13-1 hosted such stars, they might have ionized a local bubble of hydrogen, allowing Lyman-alpha light to escape. But there is a problem. Population 3 stars are hypothetical. We have never directly observed them. JWST's spectra of other early galaxies like GNZ11 show heavy elements like oxygen, proving that later generation stars had already formed. If JAIR's GS Z13-1 lacks these elements, it could be our first glimpse of population 3 starlight. Number 2. Early supermassive black holes. Active galactic nuclei AGN might have blasted UV radiation, clearing the fog. In 2013, JWST found evidence of actively feeding black holes in just 500 million years after the Big Bang. These black holes, weighing millions of solar masses, would have emitted blistering UV radiations as they devoured gas. If JAIR's GS Z13-1 harbored one, its energy could have punched a hole in the hydrogen fog. But how did black holes grow large so quickly? Current models struggle to explain it. As Dr. Rebecca Larson, a JWST team member, notes, either our timelines are wrong or there's a new physics we are missing. Regardless of the answer, this discovery suggests the epoch of reionization began earlier and was more chaotic than we imagine. Instead of a uniform lifting of the fog, the early universe might have been a patchwork of ionized bubbles, some carved by galaxies, others by black holes. JWST's findings don't just challenge theories about reionization, they force us to rethink how galaxies formed. Before JWST, the dominant model was the hierarchical universe. Small galaxies merged over time to build larger ones. But JWST's early galaxies are surprisingly massive and structured. JAIR's GS Z13-1, for example, is 1600 light years across. Small compared to the Milky Way, but enormous for its age. Its stars already weigh 450 million solar masses, suggesting rapid, efficient star formation. Even more puzzling are galaxies like CEERS 1019, home to a black hole 9 million times the Sun's mass at Z8.7. How did it grow so fast? Some theorists propose direct collapse black holes, where gas clouds implode into black holes without forming stars first. Others argue for hyper-efficient feeding in dense early universe. Then there is a crisis in cosmology, sparked by JWST. Simulations based on the standard model of physics predicted far fewer bright early galaxies than JWST has found. To explain this, some scientists suggest tweaks to dark matter behavior or the primordial gas composition. Others, like Dr. Elika Nelson, propose that early star formation was bustier and more intense than we thought, with galaxies flickering to life in violent waves. But JWST isn't done yet. In 2024, the telescope began studying JAIR's GS Z13-1 with its mid-infrared instrument, MIRI, searching for heavy elements. If detected, they would confirm that multiple generations of stars lived and died in this galaxy's first 300 million years. If not, it could mean we're seeing the universe's first starlight, a fossil from the cosmic dawn. But the biggest questions remain. Did population 3 stars exist? JWST's future spectra may finally catch their unique chemical signatures. How did black holes grow so fast? New models of gas accretion in the early universe are already in development. What ended the Dark Ages? Was it galaxies, black holes, or both? As Dr. Brant Robertson, a JWST team leader, reflects, every time we look deeper, the universe surprises us. JWST GS Z131 is a clue, but the full story is still out there. For now, JWST continues its missions, gazing back in time to an era when the universe was young, wild, and full of mysteries. With every observation, it reminds us that the cosmos is stranger and more wondrous than we ever dreamed. And who knows, the next big discovery, the one that rewrites the textbooks, could be just a photon away. Thanks for joining this journey to the edge of the space-time. If you want more cosmic mysteries, hit subscribe and let us know what topics we should explore next. Until then, keep looking up because the universe is always telling a new story.